that is interesting. Okay, we're going to work through the second of these 4 parts, at least in this version of POX Volume 1, on mechanisms for generating power law size distribution. We'll have more later on, but we're going to have this sort of little set of 4. So this is a relatively quick one, and the usage of it will come later on in the course a couple of times. But basically, the idea is we're going to take something that's distributed simply, exponentials or normal distribution, for which we have very powerful mechanistic stories. And then we'll have that variable connected to another variable through an inverse power law, and that will have a story for why that happens. And then that gives rise to these power law size distributions. So that's the nutshell. We have a couple of little intro pieces as usual. Usual characters behind the performance here. And 2 inanimate animals and 1 animate one as well. It's all in your mind, isn't it? So I'll go through the basics of variable transformation. So this is just a simple technical thing from statistics or probability theory. It'll be applied very generally, of course, but we're going to have this particular focus where the transformation is through an inverse power law. And I'll give you an example, Holtzmark's distribution, which is from the 1910s. That's kind of a curious one. And we'll talk about PLIPLO, and that's just a very quick thing at the end, but basically never go full PLIPLO. It's the wrong way to think about things. Transformation of variables, right? And of course we have another way of talking about it. The unexpected transfiguration. So we're going to go from the normals at the top, right? Oops, to the mountains of unusual size through this transformation of variables. And we're very happy with the normals. They're boring things, but we know why they're there. And there are different ways to arrive in this much more terrifying terrain, shall we say. So, 3 pieces. So, we're going to understand power law size distributions, that's what this is short for, as arising from simple distributions, exponentials, Gaussians, whatever you like, things for which we have straightforward explanations. So, exponentials arise from failure mechanisms, for example. Normal distributions, the central limit theorem, arise all over the place. And we've had our beautiful random walk story for that. And then there's just a variable that's connecting, the variables that are connected by an inverse power relationship. Groovy. Okay, so I'm going to just walk through this. So we have some random variable x, with some distribution p of x. And we have a second variable, and they're related. This is just the general story. They're related by some connected function f. And that could be all sorts of complicated things. In general, we'll think of this inverse one, so it's just a monotonically decreasing one. But this is the story you would have for the general story, right? So let's see. So we've got the probability that y is between. This is really saying between y and y plus dy, right? Probably that's between those 2 points, just that little rectangle, if you like. Well, that's a probability that x is such that the function of x gives you y, right? So there may be multiple ways to get to y from f, right? So we're talking about a function like this. So you have to sum over all possible pre-images of y, and each one of those gives you a little contribution. And it's going to be the probability of x at that point, dx. So all these little rectangles will add up as long as they're getting to y. And so this is still the same sum. And then, of course, we can say, well, this is the inverse function of y. We're summing over all those possible x's. So it's the pre-image of y. And then we have to be a little careful in here. If we do the dx, then this is this is really just, this is f prime of x, it's the derivative, and we've put in x here for the inverse function of y. Okay, so that's, we're going to work through some examples, so hopefully that will help. Right, easy to do by hand. And a picture would help here, but we don't have one in this particular little piece. So here's our example. We're just going to assume it's a one-to-one relationship, so we don't have that sum. And we're going to have this power law relationship. So let's develop this one. So it's an inverse power law, and there's some good reason for that, but we're still thinking abstractly. So we start with x. We know y is related to x with some inverse power law. So you can see where it's going to, that's where the power comes from. Right, fine. But yeah, this will come back when we go to the highly optimized tolerance and robustness and all sorts of things. Okay. So we're going to think about y large and x small. Right, we'll see how that works. But let's put these pieces together, and we did something similar for river networks when we were determining scaling relations. So we have y equals c of it, right? That's what it is. So it's just dy. Take the derivative. And then, can I do that? No. So just the derivative of x to the minus alpha brings a minus alpha down the front, and we've got x to the minus alpha minus 1. Just a simple derivative. That's this business in it, right? Minus alpha comes down the front, and then we have this minus alpha minus 1. We can rearrange this, because we're going to replace the dx and px dx. We want to get all of that in terms of dy. So it's just pushing everything around on the other side, right? So there's c times minus alpha. Here's your c alpha. There's a minus 1 on top. And we're going to have x to the plus alpha plus 1. Put this on the other side. Right? So dx is now over here, and the dy is over on this right-hand side. Then we have to clean things up and put in the expression for x in terms of y. So that is, if we go back over here, think about what we started with. So y divided by c, right? Put the c over here, and multiply both sides to the power of minus 1 over alpha. And that'll give us x. So that's what this blob is here, is y over c minus 1 over alpha. And it was already x to the alpha plus 1, so that alpha plus 1 is still there. So now we have dx, some constants. This is also a constant. Really, it's this crucial part here, y to the minus alpha plus 1 over alpha dy. So this is really, in our probability distribution, this is where the power law comes from. Okay, and that's just writing out a little more. Now we have y to the, right, so it's alpha plus 1 over alpha, with a negative sign up front. So y to the minus 1 over alpha. Just a little bit cleaner looking. Tidied up some C's and some other things. A bunch of those C's actually clean up. All right, that's good. So we're going to go back to our transformation. So all the hard work is in the Jacobian, right? The dy dx part. So this is replacing everything. Right, it's our general statement. We have this monotonic relationship between x and y, so it's just this expression. Probably that y is between y and y plus dy. It's going to be probably that x is between x and x plus dx, providing that we're in the right place, right? But y is this function of x. Excuse me. Right. Terrible. Okay, so x, we did this before. It's y over c, the minus 1 over alpha. That's a blob in there. Got my curly brace in the wrong place. And this is our dx. It's this big shmush. And I've really just highlighted the important part, right? So this is y to the minus 1 over alpha. And in here, we're going to have our y. We were thinking of y large. This alpha is positive, so y is large. This is x is small. So if you think of, in a Gaussian or an exponential, this is going to be well behaved. There's nothing going to be exploding too much here. Could be, but this is where we'll start. So if the probability of x as x goes to 0 goes to some non-zero constant, right, behaves reasonably well, course, if it's 0 there, we're in trouble. But we're thinking about things like exponentials and Gaussians. Then simply this blob at the front, this is just going to be a constant, right? This is going to 0. Think of like the middle of a Gaussian, this is just going to some constant. And really all of the work is here. Okay, so that's happening. And then so we'll have the probability of y. That should be a little subscript y there. Will be y to the minus 1 alpha, right? So that's our power law. If instead we have some scaling for p of x as it goes to 0, it's x to some beta, we can put that in as well, and we'll get some scaling like that. So it's going to depend on the alpha and the beta if it's there. But really clearly we're getting these inverse power laws distributions for y, right? So there's, yeah. And it's super exciting. Anyway, it's laid out there. That's the game. And so you can have this kind of general story, but often you want to just work through a particular one, particular example, making sure everything's kind of okay. So imagine we have some exponential distribution, right? So this is normalized properly, 1 over lambda e to the minus x over lambda. And we have the same transformation, y equals c, x to the minus alpha. Then we get the same business, right? There's some correction term, but basically straight away we can say, okay, it's going to a constant, right? P of x is going to a constant, so we know that P of y will have this form. Doesn't matter that it's exponential, right? But the dominant thing we'll see is this minus 1 over alpha. Right, and so I mentioned this before, exponentials easily come from randomness. If you're flipping a coin, some weighted coin, and the probability of the number of times, the number of flips you get before you get a head, that's going to have an exponential decay, for example. So it's a very simple kind of failure thing. So we're going to come back to this when we look at robustness, and various ways we'll look at that. But highly optimized tolerance will be the sort of core thing we'll talk about there. Why do systems mostly not explode? Right, lots of things continue along in their merry way. They get to be pretty decent size. Us, ecologies, the Earth, but now and then they fall apart, and when they do, it can be unfortunately rather spectacular. Forest fires will be sort of both a real and kind of a simplified model example for that. Okay. Example: Holtzmark's distribution. Might explain the music. So we're going to do something a bit peculiar, but if you have one of these things, it's a little bit easier. So we're just going to push the wrong buttons, or maybe think we're pushing the right buttons in our police box. And we're going to transport ourselves to a random point in the universe. Right, we probably should use the community reference here, but it doesn't matter which time. We're really worried about the location. Now, there's a lot of space, but occasionally there's a star, and it would not be ideal to transport into the middle of a star or a planet, for example. That would be not great. Never really happens in stories too much. So, but there's reality, and of course we're really trying to embrace reality here. So we're going to transport ourselves there. We're going to measure the force of gravity, which may be sort of done very nicely for us by sucking us into a black hole. Might be a bit difficult, that is. And if you do that enough, and you'll probably feel your insides will be turned around, that the distribution of the force of gravity will decay as f to the minus 5 halves. Now that is minus 2.5, which I want you to sort of just immediately be able to realize is between 2 and 3. It means it's a finite mean, but infinite variance, and second and third higher moments are all infinite. So most of the time, you're in space, pretty small. Not so bad. This is fun. We're going to do it again. Different stars all the time. Pretty cool. and you can have the adventures with the crazy person. But now and then there's a high variance, so you keep going, you will eventually, it will end poorly. So let's see if we can derive that. One little thing to do. So matter's concentrated in stars, and they're going to be the main source of gravity. Jupiter's very excited about how big it is, but the sun is large. Yeah, just for our local story here. So we're going to think about just what's happening locally around a star, and we can worry about sort of how things tail off. But if we sort of think about landing in that particular region, the probability of being a distance r from it is going to grow proportional to r squared, right? So the surface area is 4 pi r squared, right? So if you go out, make little shells going out from a point, then and little drs, so the little region where you're r away from the star is going to be 4 pi r squared times dr, right? That's going to be the volume of that little space. And we'll throw the 4 pi away because we're casual people. But basically it's proportional to r squared, right? So if we're in 4 dimensions, it'd be proportional to r cubed. If we're in 2 dimensions, it'd be proportional to r. In 2 dimensions it matters because of the gravity thing has some utility when we think about us being on our little earth ball thing, which we talked about with Zipf's law and stuff. I guess it was back over there. Maybe it was that way. It was that way. Yeah. Yeah, spatial metaphors. Gotta get it right. Okay, so boom, we're gonna say that. Right, so there's more as you get further away, right? It grows as r squared, so there's more space growing as r squared where you can be r away from the star. So it's good because, again, not so happy with landing in the star. So, this is a bit of a problematic piece. We know the galaxy thing and clumpiness, but yeah, we're worried about this local part here. Law of gravity, got it. I do have some other tarot cards about this because, that was not obvious entirely, right? That it has a decays as 1 over r squared. We'll come back to that. But Newton had some oddness there. Of course, he was off with astrology and all sorts of things. But then he finally got it right and said, let's make money. So, law of gravity. Decays is 1 over r squared, which has this, that's a nice story, right? It's proportional again to the surface area, right? It's being diffused, if you like, or thinned out in a way that's sensible. So we'll invert that. This is our inverse power law variable transformation, right? So r proportional to f to the minus half. And so the game here is we're trying to so we've sort of set up this probability distribution. You can see it's not going to be normalizable, but this is local to the star. This is reasonable. And then because that's sort of the part we're worried about, and then we're going to have the transformation between variables. It's an inverse power law, so the game is afoot, shall we say. And again, it's we could use the formula we just had, but we can just sort of work through it. So dr is just df to the minus half, so that's f to the minus proportional to f to the minus 3 halves. All right, so we've got that, and we can plonk that in. So we've got these 3 pieces. We've got the variable transformation, right? So that's an inverse power law. We've just established this, that dr is this, and then we have p of r is proportional to r squared. So p of r dr is proportional to r squared dr. We're going to put the dr in as this blob, and then we're going to replace r wherever we have it with f to the minus a half. Okay, transformation of variables. So probably the r in here, right? The r in here, that becomes something times f to the minus a half. And r is going to be small, f is going to be large. So this is something that doesn't explode too much. F to the minus 3 halves is here, right? This is from the dr. All of that blob goes here. And really we're going to leave the probability because we're going to say it's pretty much a constant close to, that's a good question, close to the star. And just plunk these things in here. So we're going to have, yeah, let's get it right. So yes, of course, one more thing. So we've got P of R is proportional to R squared. So we're going to, this is going to, this blob to the power of R squared. So that's this blob here to the power of R, to the power of 2. So this is going to be an f to the minus 1 here. This was just from the dr, so this is f to the minus 3 halves still. So we're going to have f to the minus 1 minus 3 halves, and that's f to the minus 5 halves. So maybe if you play that forwards or backwards, you'll get it right. Some heavy editing. So this is a gamma equals 5 halves, as I said. Mean is finite, variance is infinite. Shorthand for saying it. So it's what we would call a wild distribution. Right. Starting from a mild one, we get a wild one. So this is a game where usually okay to press the button and open the door and see where you are. But can and eventually will end very badly. So if you have something like floods or earthquakes or whatever it is, some other system story locally here on Earth that has these exponents, it's definitely a statistics of surprise situation, and one should be worried. I meant to edit that out. Okay. It's unfortunate. Okay, so PLIPLO. Let's talk about PLIPLO. PLIPLO, power law in, power law out. Happens. But generally, this is not how we want to hope to explain things. And certainly, because if you have a power law distribution and you mess with that and get another power law size distribution, you've pushed the game forward, backwards to this initial distribution. That's fine. Okay, but you don't stop there, and you will sort of see that now and then, or certainly in the past. So we don't want to do that, right? We don't want to explain a power law size distribution or a heavy tail distribution as being a result of another heavy tail distribution. So it's not as, what we're looking for are micro to macro stories where the micro is well understood, that has some measurable behavior, some sort of defensible behavior, and to go back to the central limit theorem, right? Little things bouncing off of each other. If we think about Einstein's 1905 paper on Brownian motion, this could give rise to this macroscopic behavior. That's very nice. That's great, right? That's, of course, gives you the normal distribution. We want to be able to do that sort of thing over and over for these power law size distributions. And as a general rule, there are many different kinds of stories that can give rise to power law size distributions, which puts them into a different game than, say, again, the normal distribution, which has this sort of beautiful big story. Usually there's some growing, there's some accumulating, there's some aggregating, but as to why a distribution might have a certain exponent, or why it's not necessarily a power law size distribution, but something maybe a log normal, or some other heavy tail distribution, different mechanism. So I will liken this to a homunculus argument, which is a fairly sort of silly business. Just a Wikipedia piece here, right? So this is right, that you sort of try and explain vision, but more generally explain thinking, that there's a little person inside your brain that does the thinking, because that seems like a good explanation, but then there's another little person inside them. So not ideal, right? So you don't want to sort of fall into that category. Anyway, brains are tricky, and of course, unfortunately, we use our brains to think about them, so it seems like a bit of a dangerous game. So please don't do this. Slapping is metaphorical, obviously. Unless your cat is doing it to you, I suppose that's okay. So what you want is MeWo, speaking of cat sounds, mild in, wild out. That's what we want, right? That feels like we've and of course, measuring the micro behavior and kind of really nailing that down and looking at it and saying, oh yeah, this is really what's happening locally. And we did the simulation, or we did some math, and we're able to scale that up and say, oh, look at this macroscopic behavior. We understand it. So, and of course, that's about mechanisms. All right. That is part 2, of really part 10,003, but we are going to have these 4 big pieces on power law mechanisms in terms of sort of simple, somewhat simple mechanisms, I suppose. They'll vary in nature as to whether they're mechanisms or things where we might say there's an optimization in action, but we don't actually really explain it. We sort of just kind of invoke evolution and Darwin, people with beards, but some are more explicit in the fact that they're mechanisms. But we'll see some other stories for why why systems have these statistics of surprise.